Okay, so let's talk about solubility of ionic compounds in water. Okay, so in other words, water solubility of ionic compounds. Okay, so first of all, we want to talk about what this dissolving is for ionic compounds. Okay, so we're going to talk about, to explain this, we'll use an example. We'll use sodium chloride because that's the most common ionic compound we come across in our day-to-day lives. So if you have sodium chloride, solid, and then some water in the liquid phase, okay, this is our undissolved state. Undissolved state. And then if you put these things together, then you're going to get the dissolved state. But in the dissolved state, you're not going to get the sodium chloride like solid. What is going to happen is the individual cations and the anions are going to be separated and going to get solvated or surrounded by water molecules. So as a result of that, you're going to get sodium plus ions and then Cl minus ions. I'm writing aqueous or AQ in short within parentheses to indicate that these ions are surrounded by water molecules. Okay, so so for an example, if you take the sodium ions, which are the cations, okay, what is going to happen is sodium. So let me first say that this is our dissolved state. We should make that distinction. This is our dissolved state, or in short, I'm going to call this D, and then undissolved state is UD. Okay, anyway, so what is meant by sodium plus aqueous, so Cl minus aqueous, is our cations and the anions are surrounded by water. Okay, so if we have a positively charged ion, let's say this is our sodium ion in this case, okay, and this sodium ion is going to get surrounded by water molecules. The water molecules are going to arrange around the cation. It's going to look something like this. Okay, and then there's a reason why oxygen is facing the or interacting with the cation. The reason is, if you think about the polarity of the water molecule, the oxygen has a partial negative charge, okay, indicated by the arrowhead of the dipole moment, net dipole moment, and that is going to interact with the positive charge. Okay, partially negative charge arrowhead interacts with the positively charged cation. So it's going to look something like that. Okay, and these are called ion dipole interactions. Okay, these are called ion dipole interactions. Okay, the same thing happens with the negative charge as well, actually. Okay, so we have the negatively charged ions, or the anions, in this case chloride, and they are going to get surrounded by water molecules. This time I'm going to only draw the dipole moments, but in this instance, the arrow tail, which is partially positive, will interact with the negatively charged ion, because opposite charges attract each other. That's the reason why arrow tail is interacting, not the head is interacting in this case. Okay, so if you want, you can draw the water molecules as well. Okay, just for the completion of our picture, you can see the water molecules are getting ordered. Okay, this is also called the ordering effect of water. Okay, these individual ions causes the water molecules to order around these anions and the cations, and this is called the ordering effect of water, or solvent ordering effect by the cations and the anions. Okay, this is called the solvent ordering effect. Solvent ordering effect. Okay, the solvent ordering effect is going to decrease the number of configurations in water. Okay, this phenomenon decreases the number of configurations in water. Okay, so yeah, the idea of this particular whiteboard is to understand what is dissolving of an ionic compound, the dissolution of an ionic compound. Okay, so when the ionic compound dissolves, the solid ionic compound dissolves in water, you're gonna get the individual cations and the anions that the ionic compound was made of. Okay, and these ions are going to get surrounded by water molecules with ion dipole interactions, like shown here, and this causes the water molecules to get ordered, and which is going to decrease the number of configurations. Okay, and then at the same time, I want to mention that in the undissolved state, okay, you have mainly ion interactions, cation and the anion interacts in the solid. Okay, ion interactions and intermolecular forces between water molecules. And when it comes to the dissolved state, okay, you are going to have ion dipole interactions. Ion dipole interactions. Okay, so so just to be clear, here we have ion interactions between sodium and chloride ions and intermolecular forces, and then in the dissolved state we have ion dipole interactions. I just want to make that note before we move on to the next page. Okay, now with that, what I want to do is I want to talk about the possible situations. All right, so dissolution of ionic compounds is a process that depends on two factors. Okay, and those two factors are potential energy and the number of configurations. Okay, the mixing or dissolution of ionic compound, solubility of ionic compound. Let me see, the process of mixing. Let me have a color. The process of mixing. Okay, or let me write it in a different way. The favorability of the dissolved for the undissolved state depends on one, the potential energy, two, the number of configurations. Okay, and this is what we have in the PEC diagrams. So based on this, we can have four possible situations. If we have, let's start by drawing this. Here's one, potential energy, number of configurations. Okay, if both potential energy and the number of configurations favor the dissolved state, that means dissolved state has a lower potential energy and a higher number of configurations like this. Okay, then this is going to be always soluble. Okay, always soluble because both potential energy and number of configurations favor the dissolved state. Okay, and then interaction strengths wise, we can say that we have stronger interactions. Okay, interaction strength. Interaction strength. Okay, we have strong interactions in the dissolved state compared to the undissolved state. And then we can also say that the ion dipole is going to be stronger, because in the dissolved state what we have is ion dipole interactions are stronger than the ion interactions in the undissolved state. And also we can talk about the effect of temperature. Increase in temperature will favor the state with higher potential energy, which is the dissolved state here. Therefore, it will decrease the solubility. Okay, now that is about that PEC diagram. Another situation is we can have let me see if I can have this a little bit separate from the other one. Okay, if we have the undissolved state favored by both number of configurations and the potential energy, that means in this quadrant compared to the dissolved state, then both potential energy and the number of configurations favor undissolving or not dissolving. Therefore, this is going to be always insoluble. And then interaction strengths, strengths will be greater in the undissolved state compared to the dissolved state, because undissolved state has a lower potential energy. Okay, this means the ion interactions are stronger than the ion dipole interactions. And also, if you increase the temperature, that will slightly increase the solubility, because increasing temperature favors the state with high potential energy. Therefore, that is the dissolved state here. Therefore, it's going to increase the solubility slightly. Okay, and that's the second situation. And then if we do another one, let's say that we have our dissolved state at higher potential energy, higher potential energy and higher number of configurations compared to the undissolved state. Okay, then the potential energy does not favor the dissolved state, but the number of configurations favor the dissolved state, because you have a higher number of configurations. If you have a situation like this, this is going to be soluble only at high temperatures. Okay, because the dissolved state has a higher potential energy. And then if that is the case, if this is the case, then the interaction strengths, strengths wise, we're going to have stronger interactions in the undissolved state, because it has a lower potential energy than the dissolved state. And then this means the ion interactions are stronger than the ion dipole interactions. Okay, and like we mentioned before, increase in temperature will increase solubility, because anyway, we can write that if you want to. Increase in temperature will increase the solubility. Okay, there's one more situation. Okay, potential energy, number of configurations. In this case, we have our dissolved state in this quadrant. And if when it comes to this quadrant is favored by the potential energy, because it has a lower potential energy, but not favored by the number of configurations, because that has a lower number of configurations. If you have a situation like this, this is gonna be soluble only at low temperatures. Okay, the interaction strength will be stronger. Interactions are stronger in the dissolved state compared to the undissolved state. How do we know this? Because the dissolved state has a lower potential energy. Lower potential energy means stronger interactions. And then this means the ion dipole interactions are stronger than ion interactions. And then lastly, we can talk about the effect of temperature. We already did kind of in the first part, in the first point, but anyway, increase in temperature will favor the state with high potential energy, which is going to be the undissolved state. Therefore, increase in temperature will decrease the solubility. Okay, so this summarizes the 4 possible scenarios for dissolution of ionic compounds in water. That's it. I'll see you guys in class. Bye, everybody.